Once we've got heaps, it's actually really easy to come up with an optimal sorting algorithm. And what I mean by this is a sorting algorithm that will take n log n time. That's a linearithmic algorithm. It's not an algorithm that is used much in practice because it's a two-pass algorithm, and therefore it's actually got worse constants than algorithms that we do use in practice, like merge sort and quick sort. You'll learn those in your algorithms class, CSE 321, 421. But it's nice to see an optimal sorting algorithm, so let's look at it. The basic idea of heap sort is to take an array and turn it into a max heap, and then repeatedly remove the max, not actually deleting it from the array, we're going to leave it in there. And if we do that, delete the max over and over and over again, what we'll get is a smaller and smaller heap and a bigger sorted array. And so when we're done, we will have the whole thing sorted. This is going to work out for us really well because we can take an array and turn it into a heap in n log n time. That's logarithmic for each element. The basic idea is just to sync them all. How many are there? N. How long does sync take? Log n. So the total time is linearithmic. Well, then we're going to delete the max n times. Delete the max takes log n time. We're doing it n times. So again, linearithmic. So linearithmic plus linearithmic, linearithmic. I'm going to walk through a demo from the textbook. We're starting with an arbitrary array, and we are going to ignore the 0th element of that array. We don't know what the order is. We do not have a complete binary tree just because it's an array. And all we have to do now is get it in heap order. So how are we going to do that? Well, we're going to look at all of the leaf elements and observe that those things can be thought of as little tiny one-node heaps. And what we're going to do is progressively create bigger and bigger heaps starting from the bottom up. It's actually very simple to code, but it's interesting to see what happens. So we just need to start at in div 2. That'll be 5 in this case. And what we're going to do is sync the 5th element, creating a 3-element heap. Then we'll go back to 4, and we'll sync it, creating a 3-node heap. Then we'll go to 3 and sync the 3rd node here, creating again a 3-node heap. We then sync 2, which will give us a 7-node heap. Finally, we're going to sync S, which will give us our last heap. It's got 11 nodes in it, and we're done. So think about how long this takes. We're actually going at in div 2, and then we're syncing down for each of those. If you take sync to be worst case logarithmic, that's in div 2 times log of n. After heapification or heap construction, we next are going to do sort down. The sort down phase is simply going to delete the maximum over and over again, leaving it in the array. So when I swap x and e, we've morally removed x from the array, creating a smaller heap. We then sync 1 down, and that may take a while. In general, it's going to take logarithmic steps to get there. Note that with the heapification, we can get lucky and things may not swim very far. But in general, in this sort down, we're always taking something that's at the bottom, putting it at the top, and it's generally going to have to sync all the way to the bottom again. Let's take the next element, t, and we'll remove it from the array. And now we have to sync down e. We take the s and sync down e. We take r, sync down m. That simulation is so boring, I just skipped to the end. Let's look at something more fun. Heap sort, that's the heapification, and now sort down. So note, heapification was so fast you barely even noticed it. Look how long this sort down takes. I just have to keep talking and talking and talking. I'm bored with this one too. Of course, all of our visualization software works on heap sort as well, and you can see that it's a pretty fast algorithm. So with random data, again, watch the random, you can see the 2 phases here. That's heapification, and now sort down. Coding heap sort is really easy if you have sink and swim. In the first phase, you just start halfway through and sync every element. So we're going to sync 5, 4, 3, 2, 1. In the second phase, we're simply going to exchange every element with the end element and then reduce the number of elements that we're considering to be in the heap. And then we're going to sync down the first element. And so here we're syncing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're done. Sunk them all down. There's the whole implementation. It's just straightforward once you understand syncing. So heap sort has optimal performance. You'll see in your algorithms class, we can't do better than linear arithmetic for comparison-based sort. It also works in place. We don't need a separate copy of the array to work in like we do with merge sort. However, this algorithm is not used much in practice because it has really lousy cache performance. The inner loop is long and it's not stable. We end up swapping elements all over the place. So there's really very few use cases where you would want this particular algorithm.